So we have done addition and subtraction in the matrix operations. We also learned some names of matrices, such as the zero matrix and the identity matrix. We discussed the subtraction property last time, but I would also like to discuss a whole lot more properties, and so that's where we're going to go with this time. These properties we've all seen when we talk about the real numbers. So probably an introduction to your college algebra class, you probably discussed these properties, and you've probably seen them again along the way, but this is the first time you've seen them since then all together again. They seem pretty trivial at this point, but you're going to see very shortly why we are discussing them now, because not too long from now, we're going to see that some of them don't hold true when we are discussing matrices. So the first one is the commutative property, saying that we can switch the order of the addition of these. I can take matrix A and I can add it to matrix B, and if I were to switch it around, matrix B plus matrix A, it'd be the exact same thing, right? Easy enough, because when I add two matrices, I just add each entry, so it doesn't matter if I switch those around. The associative property says if I'm doing an addition with three different matrices, it doesn't matter if I add A plus B first and then C, or if I add B plus C first and then A. It doesn't matter. It doesn't matter, again, because matrix addition is just adding each entry. So I can rearrange the order of the entries in my addition format and it not cause a problem. Okay, scalar multiplication. It means we can multiply one scalar through and then the second one through, or I can multiply the scalars first and then distribute them through the matrix. If I wanted to distribute one scalar through two matrices where I'm adding, it doesn't matter if I add the matrices first and then distribute my scalar through, or distribute my scalar through each matrice individually and then add them up. All right, likewise, if I'm adding two scalars and then multiplying them through a matrix, it doesn't matter if I do my addition first or if I do my multiplication first and addition second. The additive identity, and this is why it's important that we defined the zero matrix, is if I add a matrix to a whole bunch of zeros, I am, of course, going to get my original matrix. And this is true, again, with the whole numbers. If I wanted to add 5 plus 0, I would still get my original number of 5. That's why it's called an identity. Okay? And then the additive inverse. So this is kind of combining, again, a scalar here, a scalar of -1, meaning if I add matrix A and the negative of matrix A, I'm going to get my zero matrix, or a matrix full of zeros. And of course, order doesn't matter because the order of addition doesn't matter. So again, it seems trivial here. Of course, these are the way they are. Well, again, just stick with me for a moment and I'll prove to you that these things aren't always trivial when we're discussing matrix operations. Okay, which leads me to that. The next matrix operation is multiplication, or the product of two matrices. Well, most people, when I first introduced this, thinks it's going to have the same properties as before. Instead of just adding or subtracting each entries, then I'm going to multiply two entries. That is not true. Matrix multiplication is very different than matrix addition and matrix subtraction. Okay, so first and foremost, notice that I've stricken out the matrices have to have equivalent dimensions. That is not true when I want to multiply two matrices. Okay, what the dimensions need to be is the number of columns in my first matrix needs to match the number of rows in my second matrix. And I've put a very specific example here so you can see. So if A is m rows by n columns, and matrix B is n rows by p columns, I need this and this dimension to match up. So this number of columns needs to match this number of rows. Then, when I do that, I am going to end up with a matrix of dimension m times p. So notice my product here is dimension m times p. So that's how the dimensions work. So first, before you try and multiply matrices, you need to match this number of rows times this number of columns. Because when I multiply these, this is how we do it. We multiply the entries in the rows of my first one times the columns of my second one. So I multiply each of those entries and I sum up that math right there. So instead of me speaking hypothetical, let's actually do this here. Let's try and find the product of A times B. But before I actually jump into it, let's see if my dimensions match. So the dimension of A is 2 by 2. The dimensions of B is 3 by 2. So if I were to multiply these, I need to make sure that this dimension matches this dimension. In this example, they do not match. So I actually cannot multiply A times B because my dimensions are not in the format that I need them to be in. Okay, so let's try and find one that does work. So here I've defined new matrices. I didn't need to, but I've defined new matrices. So let's see, I've got 4 different examples here. Let's see how many of these 4 I can do, and let's see what actually this matrix multiplication looks like. Okay, so again, I'm doing A times B, so let's look at the dimensions of this A. It is 2 rows by 3 columns, and this B is 3 rows by 2 columns. So I need this number to match and I need this number to match. They do. That means I can actually multiply these here. So the way that this works is I'm going to take this row to start out with and I'm going to multiply it by this column. So I multiply the row of the first by the column of the second. So I'm going to write all of this out here. Okay. Now, I know that I'm going to end up with a 2 by 2 matrix. So I'm going to have 1, 2, 3, 4 entries. This first yellow that I've highlighted here, let me put that in this yellow here. So I multiply each entry. So I have 3 times 1. So this one and this one. And I add that to, next, my 1 times 3, and I add that to my negative 1 times my negative 2. So again, I am partnering this up with this here, and that's what's going into my top left. Okay? So that is one of my 4 entries. I need to probably make this guy bigger. All right, next, I need to take my top row again, and I'm going to multiply it by my second column. So when I shift over a column here, that means I'm going to shift over a column there. So I have 3 times 6 plus 1 times negative 5 plus negative 1 times 4. So again, I took 3 times 6, went here, 1 times negative 5, went here, and negative 1 times 4. Okay, now let's move on to my next. So I'm going to move down a row here. So I move down a row here, and I'm going to partner that up with this column right here. So I have 2 times 1 plus 0 times 3 plus 3 times negative 2. And last, I have this row, so bottom row, right column. So bottom row, right column. 2 times 6 plus 0 times negative 5 plus 3 times 4. So all I need to do now is simplify this basic math. So let's see how much multiplication and addition we can get in our head. So let me move this guy out of the way here. Okay, so that is equivalent to 3 plus 3 plus 2. So that's 8. Here, 18 minus 5 is 13, minus 4 is 9. Here, 2 plus 0 minus 6 gives me negative 4. And 12 plus 0 plus 12 gives me 24. And notice I ended up with a 2 by 2 matrix. So we have just done our first example of matrix multiplication. We found the product of A times B. Okay, when we come back, I'm going to be working through these other examples that I have listed here. So I need to find B times A. Let's see what happens in that situation. And then also some other examples over here, A times C and B times C. So that's going to be covered in the next video.